Okay, let's begin. So last time we started studying partial orders and we were looking at various definitions and with examples, of course. So today we'll continue that. So remember, we ended with definition of a chain. A chain is a subset of a partially ordered set which is linearly ordered. Okay, so let's go back to some examples and see what are chains. So for example, in M3, can you describe one chain? It's on the screen. 0, 0A1, that is a chain. 0B1 is another chain. 0C1 is another chain. Just 0 is a chain. 0A is a chain. 0B is a chain. 01 is a chain. Yes? Okay. Now, a completely orthogonal concept is that of an anti-chain. So, in chain, any two elements are comparable. In an anti-chain, no two elements are comparable. Of course, except for an element with itself. Yeah, we have to exclude that possibility naturally. So, no two distinct elements are comparable. So, can you tell me in this M2 or power set of 2, what are, can you give me an example of an anti-chain? Singleton 0 and singleton 1. That is an anti-chain. Then so is any singleton. Every singleton is also a chain. In M3 we have got 3 element anti-chain A, B, C. In N5, what is the maximal size of an anti-chain? 2. It is either AB or AC. Okay. Okay, good. So far so good. So now that we have seen these concepts of chains and anti-chains, now we would like to understand what are the maps between partially ordered sets. So naturally, whenever we study morphisms or maps, then they should preserve the mathematical structure. So what will that be called? You already know the answer. Monotone maps, order preserving maps. Yeah, if P1, see, this is another practice. Yeah, even though these are two different relations on possibly different sets, we will use the same notation less equal. Yeah, we won't use different notations all the time because it will be too cumbersome to write down. If these are posets, say that a function, so right now it's just a function f from P1 to P2 is a monotone map, monotone or order preserving if for all xy in P1, x less equal y implies f of x less equal f of y. It preserves order. What will be the definition of order reflecting? Right, so let me use red color. So order reflecting, the same definition with, you only change this implication to reverse. So order preserving, order reflecting. Reflecting as in you see in the mirror, yeah, x is less, so fx and fy are comparable, then x should be less equal y. That is order reflecting. Okay, then there is something very interesting about this. So for example, in linear orders, if you have a bijective order preserving map, then automatically it's an order isomorphism, correct? The same concept doesn't hold here. So let us look at an example. So consider this 0, A, B, 1. I am writing M2. Now M2 to 4 element chain. Now this is 0, 1, 2, 3. Okay. Now I will describe the map using red color. So 0 maps to 0, A maps to 1, B maps to 2, and 1 maps to 3. Now tell me, is this bijective? Yes, this is a bijective map. Does it preserve order? Yeah, 0 is less than A, 0 is less than 1. 0 is less than B, 0 is less than 2. B is less than 1, 2 is less than 3. A is less than 1, 1 is less than 3. It is order preserving, but it is not order reflecting, because 1 is less than 2, but A is not less than B. So this is a bijective map. Bijective monotone map that is not order reflecting. So what should be the definition of order isomorphism? It should be bijective, it should preserve order, and it should reflect order. Okay. So let us write that definition down. So say that F from P1 to P2 is an order isomorphism if F is bijective, monotone, and order reflecting. Now this concept that order preserving and order reflecting together is so important that even when our map is not bijective, we still want to give it a name. So let me define that. So say that an injective map F from P1 injective monotone map is an order embedding if it is also order reflecting. See, embedding, this word, you embed, you don't change your identity, you just go and sit somewhere else. Right? So therefore it should be order preserving, order reflecting, and injective, but not necessarily bijective. So a surjective order embedding is an order isomorphism. Yeah, so what is the difference between order isomorphism and order embedding? Only that it may not be a surjection. That's all. So in the previous on the previous slide, if I had another point here, yeah, if I add a 4 here, then is this an order embedding? It is still not order reflecting. But if I embed a chain of 3 elements into a chain of 4 elements, then it is an order embedding. Okay, so order embeddings are important because they capture the essence of isomorphism. If you have an order embedding, then what happens, that the image of that function is isomorphic to the domain. Okay, so if F is an order embedding, then F from P1 to F of P1 is an order isomorphism. Okay. Any questions so far? I have added a few more examples. Yeah, I mean, maybe you were thinking last time why it is called a 2 crown. This is a 3 crown. When you keep it on the desk, it will look like a crown. Yeah, 3 points at the bottom and 3 points at the top, and they are arranged in crown shape. It feels like they are arranged in a circle. Then one more thing I have added, this Cartesian product n cross n with respect to less equal, where less equal is simply pairwise, right? n1 m1 is less equal n2 m2 if the first components are comparable and the second components are comparable. Okay. Now we want to study a bit more properties of nicer properties of partially ordered sets. Okay, so therefore let us define something more. So we are going to define order-theoretic lattices. There will be two definitions of lattices. The first one is order-theoretic, the second one is algebraic. And in the tutorial you are asked to prove that both these definitions are equivalent. Okay, so say that because it's a lattice, we'll use the letter L. For a poset, we use the letter P. Say that a poset is a lattice if for any x and y in L there is A in L such that now there are two properties. Yeah, first property is that x is less equal A, y is less equal A. So it is, so A is an upper bound of x, A is an upper bound of y. And second thing, whenever x is less equal b and y is less equal b, then A is less equal b. So it is the least upper bound. So amongst the common upper bounds of x and y, A is the least one. So this is the least upper bound. Or join. Okay, join is the correct technical name for this. And how do we write this? We write it as join x, then small v, and then y. And dually, see, I am writing the word dually. Dually because if I invert L upside down, then the join in that inversion, if it exists, it will be the meet in this case. So the least upper bound in L op would be the greatest lower bound in L. Okay, so and dually there is a C, I mean a C, maybe it will confuse you. There is C in L such that C is less equal X, C is less equal Y. And can you tell me what next? Whenever D is less equal X and D is less equal Y, then D is less equal C. Okay, so this is called the greatest lower bound, GLB, or meet. And what do we denote it by? X meet Y. Okay, it takes some time to get used to this notation, join and meet. So what we are saying is that for any two elements in your lattice, there should be a greatest lower bound and a least upper bound. So what does the picture look like? If I have X and Y, they are incomparable, then X join Y sits here and X meet Y sits here. So basically look at this shape, this particular shape which I am highlighting using red. This particular shape is the shape of join, it's inverted, and the bottom shape is the shape of meet, inverted. Understood? So that's easy to remember. Okay, so let us go to the first slide and determine which ones are lattices. Is n less equal a lattice? For any two elements, does there exist a least upper bound and a greatest lower bound? What is the least upper bound? No, least upper bound. So it is the max. Okay. So every linear order in fact is a lattice. So linear orders are lattices. Meet is max, meet is min, and join is max. So we have plenty of examples of lattices. So I mean rationals, reals, they are all linear orders. So in particular they are lattices. Every ordinal is a lattice. Then integers are a lattice. In number theory, I should warn you, in number theory there is a concept of integer lattices, which is simply z cross z or z cross z cross z sitting inside the vector space r to the power 2 or r to the power 3. They are called as integer lattices. They have a very different purpose. They are lattices in our sense, okay, but our definition is different. So don't confuse these lattices with number theoretic lattices. Mathematicians tend to use the same notation and same terminology multiple times because they just feel that it's more natural. Okay, what about divisibility? Is this a lattice? Given two different natural numbers, does there exist their least common divisor? Greatest common divisor and least common multiple. Yes? So therefore this is here meet is GCD and join is LCM. Okay, so GCD and LCM are simply abstracted in the form of meet and join. Okay, what about power set? Does there exist a maximal common subset of two things? Two subsets? What is it called? Union and intersection. So very good. So meet is intersection. So smooth out that triangle, and join is union. Okay. What is meet in the case of subspaces? Given two subspaces, what is the largest common subspace? Their intersection. Common, yeah. And join is their sum. Yeah, it is the subspace generated by their union. Yeah, it's not union. Union of two subspaces is not a vector space, right? Okay. Well, in case of n cross n, meet and join will be taken pairwise max and pairwise min. Those are joins and meets, right? I'm not writing that. What happens to the two crown? What is join of A and B? It does not exist, because the join of A and B, I mean they both have common upper bounds, C and D, both of them are common upper bounds, but there is no least one, so not a lattice. No crowns are lattices. What about M3? Is it a lattice? What is meet of A and B? What is meet of A and C? 0. What is join of A and B? What is join of 0 and 1? Okay, so this is a lattice. I am not going to draw. This is also not a lattice. Yeah, I mean the 3 crown is not a lattice. This is M2, so this is a lattice again. N5 is a lattice. Then this picture now. Yeah, let me name them A, B, C. I mean maybe 0 AB. This one is a meet semilattice. Meet semilattice in the sense that it only has meets of elements, and the bottom one is a join semilattice. Okay, so this one has meets. It doesn't have join of A and B. Right? A and B do not have any common upper bound, so you cannot find the least one. And this is a join semilattice. Okay, so we have studied all the examples so far. Yes?
Second example of n cross n, if they are 2, 3 and 3, 2, how will you define meet?
2, 3 and 3, 2, then the meet would be 2, 2, because you are taking minimum of 2 and 3 and minimum of 3 and 2, and in both components you take maximum, so the join will be 3, 3. So far so good. Let's go ahead. So this is the order-theoretic definition. So given less equal, then we require that every pair of elements has a least upper bound, which is the join, and it has meet. Now I will define the algebraic lattice. It is a structure, I mean an algebraic structure of this form. It is a set together with two binary operations defined on this. Is an algebraic lattice if first one, meet and join are associative. Associativity, all of you know what I mean. A join B join C is equal to A join B join C. Maybe I should write it down for all A, B, C in L. A join B join C is equal to A join B join C, and similarly for meet. Second one, meet and join are commutative, means for all AB in L, A join B is equal to B join A, and a similar property for meets. And third condition is that they are idempotent. Idempotent means they have the capacity to generate itself, the potency to generate itself, yeah, idempotency. So, which means for all A in L, A join A is equal to A, which is equal to A meet A. Take the operation with itself, it generates itself back, idempotent. And fourth property, now so far those two things do not really interact with each other, those two operations. Now they should interact. So these are called absorption laws. So there are two absorption laws. First one is A meet B join A is equal to A, and A join B meet A is equal to A. So B doesn't matter. Yeah, I mean for all AB, we have these two absorption laws. So this is an algebraic lattice. It doesn't give you any intuition where those elements are sitting because there is no less equal. How do we define less equal from this? So define A less equal B if and only if A meet B is equal to A if and only if A join B is equal to B. So without even this, please observe that A meet B is equal to A if and only if A join B is equal to B. That holds. That if and only if holds. If these two things hold, then we say that A is less equal B. Actually, I should be a bit more careful. I should not say if and only if. I should remove this second F. If. Yeah, I mean these two conditions are equivalent. A meet B is equal to A. So it's like, what is the meet? Meet is the minimum. In this case, meet is minimum. A and B are comparable if their meet is the minimum and join is the maximum. So that's what we have written. So observe that in the order-theoretic definition of lattice, given an order relation, we could define meets and joins. Now here we are doing the reverse thing. We could define, given meets and joins, we could define the order relation. Understood? Okay. So the examples are exactly similar because you are going to prove that they are equivalent. Algebraic and order-theoretic definitions are in fact equivalent. Now that we have seen this, sometimes we also need an extra property. So say that L meet join is a distributive lattice. I mean it is already a lattice. When do we say it is distributive? If for all ABC in L, the distributive laws hold. You know distributive laws? Yes, so A join B meet C, what should it be? A meet C, join, and the other one, A meet B, join C is equal to A join C, meet B join C. Both these distributive laws hold. Okay, so let us look at one example. So let me go back to the first slide. Let us look at M3. Okay. So in M3, tell me what is A meet B? 0. And if I take its join with C, what will I get? Now tell me what happens when you take A join C. Now take its meet with B join C. So therefore the whole thing is, so these are not equal. So M3 is not distributive. Okay, so this is not distributive. And similarly, I invite you to verify that N5 is not distributive. Both of these, M3 and N5, are not distributive. And in fact, there is a characterization of distributive lattices in terms of M3 and N5. So let me write that. Okay, for before that I need just one more definition. Given a lattice L meet join, say that a subset L prime of L is a sublattice if for all A and B in L prime, A meet B belongs to L prime and A join B belongs to L prime. You have seen this in linear algebra. Yeah, what is a subspace? That sum of any two elements also lies there and scalar multiple lies. So it should be closed under algebraic operations. I am writing exactly the same thing. Okay. So A meet B is in L prime and A join B is in L prime whenever A and B are in L prime in that subset. So that is the definition of a sublattice. So now there is a theorem which we are not going to prove, but it is very easy to prove. A lattice L is distributive if and only if it has no sublattice isomorphic to M3 or N5. So actually M3 and N5 are the only two bad examples. Otherwise it's always distributive. Yeah, but please be careful. This is a very tricky statement. It says that there should not exist 5 elements which have the configuration of M3 or N5 as a sublattice. As a sublattice, this is a very important and tricky part. So that means if I choose those ABC in M3 and 1 and 0, then whatever this A and B are, their join should be this and not something else. For example, yeah, I mean I'm giving you an example of a sublattice. So if I consider a vector space V and I consider its power set with respect to subset relation. Okay, now E is the collection of subspaces, a sublattice of the collection of subsets. Is my question clear? My question is this. If V is a vector space, then E is sub VF subspaces a sublattice, we have seen they are both lattices. Sublattice of the power set is the question clear now? Is it a sublattice? No, because what happens in the power set, the join is union, and in the subspace lattice the join is addition. So the operations are different. So that's why I said be careful with the word sublattice. It is not. Yeah, so the answer is no. Okay, so this is your characterization. It's very easy to prove, but we will not prove it. But there is one word which I haven't described yet. Yeah, that's isomorphism. Let me do that. So what is a lattice morphism? So given L1 meet join and L2 meet join, lattices, yeah, given lattices L1 and L2, say that f from L1 to L2, a function, yeah, I mean this is just a function is a lattice homomorphism if for all xy in L1 f of x join y is equal to, please complete, f of x join f of y. See, this is the join in L1, the right hand side join is in L2, and f of x meet y is equal to f of x meet f of y. Okay, so it is a lattice homomorphism. That is what we are defining. And how do we define a lattice isomorphism? Well, instead of just saying a function, I add the word bijective. That's all. A bijective lattice homomorphism is a lattice isomorphism. Okay. So that's all I wanted to say about lattices. In the next week we will study Boolean algebras, and Boolean algebras are a specific subclass of the class of lattices. They are distributive lattices, but they also have one more nice property, that they are complemented. Every element has a complement. Before that, let us start studying about one more equivalent of the axiom of choice, and that is called Zorn's lemma. But I won't describe that directly. I am going to give you an exercise. Yeah. So say that a function f from R to R is additive if for all xy in R fx plus y is equal to fx plus fy. Give me an example of an additive function. For example, fx equal to x. Any other example? Any linear function. Fx equal to ax plus b. Ax, not plus b. Yeah, plus b will create a problem. For any a in real numbers, okay, fx equal to ax, this is linear. Give me one more example which is not like this.
If it's an integer x and it's not an integer x,
How do you describe, how do you distinguish? So you want to say that if I know the value of f for all integers, then I don't know the value for other things. Let me give you something. So what happens when I want to say f of x by 2? F of x by 2, can you prove that it is actually equal to f of x divided by 2? How?
f of x by 2 plus x by 2.
Yes, because of additivity.
Okay,
Yeah,
rational.
because f of x by 2 plus x, plus x by 2 is equal to f of x, and by additivity this is equal to 2 times f of x by 2. So therefore, if I know the value of 1, f of 1, so therefore if I know f of 1, then I know value of f of q for each q in q. Do you agree with this? Because f of q is going to be q times f of 1. Okay. So far we know the values of this function for rational numbers. What about an irrational number? Choose your favorite irrational. Pi. Okay, fine. So what can we say about f of pi? Is f of pi fixed if I know f of 1? No. Yeah, obviously not. So I can define f of pi equal to, let's say, c. But then if I know f of pi, then what else do I fix simultaneously? Do I know the value of f of pi by 2? So all the rational multiples of pi I have fixed. But not just that, because of additivity, I have also fixed the value of f of 1 plus pi. Okay, so let us recap what we have said so far. So if I know f of pi, then I know f of a plus b pi for a and b in rationals. Yeah, what will it be? It will simply be f of a times f of 1 plus b times f of pi. Okay, but how many such a plus b pi's can there be? Only countably many, right? Because a's are rationals, b's are rationals, so only q square many. So countably many. But how many real numbers are there? Uncountably many. So is this going to fix the value of root 2? No. Yeah. So therefore, if I add root 2, if I say a plus b pi plus c root 2, then again I can do the same thing. I can take the vector subspace of real numbers. Yeah, I mean vector subspace, Q vector subspace. Yeah, rational numbers are a field. So these are basically linear combinations of linearly independent elements. 1 and pi are linearly independent over Q. 1 pi and root 2 is also a linearly independent set over Q. 1 pi root 2 root 3 is also another linearly independent set. All of you can prove this, I hope. These are linearly independent. So we are treating real numbers as a rational vector space, and if by some magic I know the maximal linearly independent set, then for each element of that linearly independent set I can assign a value randomly, and then every real number can be written as a finite linear combination of elements from this maximal linearly independent set. What is this called? Maximal linearly independent subset of a vector space? A basis. So if I know basis, a basis, yeah, I mean basis is not necessarily unique, all of you know that. If I know a basis of reals as a rational vector space, then I can solve this problem. For every basis element, I will randomly assign one value, one real value, and then that will define a function. The question is, do I know such a basis exists? Okay, so I am not going to write anything over here, yeah, that apart from this, that if we know a basis for RQ, yeah, I mean reals as a vector space over Q, B, then any function G from B to R can be extended to an additive map F from R to R. Why? Because every element in real numbers is a finite linear combination of basis elements. So therefore I can write that F of R1 B1 plus R2 B2 plus dot 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 RK BK, what will I say? It is R1 of G of B1 plus R2 of G of B2 plus RK multiplied by G of BK. Yeah, where RIs are from rationals and BIs are from the basis set. Okay, so what do I know so far? That if I know that a basis exists, then I can find a non-trivial, yeah, I mean this is a trivial additive function, I can find a non-trivial additive function. The question now is how to construct a basis for RQ. Okay, now can we do it manually? Yeah, I mean I say one is the element which generates rational numbers, then I add pi, then I add root 2, then I add root 3, then I add root 5, then I list all the algebraic numbers like that, and whatever are not linearly dependent on the already chosen ones, then I can add that. Yeah, if I get a new element, new real number which is not linearly which is linearly independent with the already chosen set, then I add a new element. But once I add, then again if this set is countable, then I will always get something which is not linearly which is still linearly independent with the original set, so I add that one also, and this process actually never ends. So I need to go beyond finite. What do we call it? Transfinite. So I need a transfinite way of building this. So one simple way of doing this is use well ordering theorem. Correct? By well ordering theorem, real numbers can be well ordered. So what do? I choose x naught. X naught is the 0th element in that list. X naught, is it 0? Is it linearly independent? Is singleton x naught linearly independent? If it is non-zero, then it is linearly independent, yes. Then I choose x2. Is x1, x2 linearly independent? If it is, then I keep x2. If it is not, then I exclude it. And similarly, I keep on adding more and more elements. I will go through all x1, x2, xn. Then I will go through x omega, then I go to x omega plus 1 and so on. If it is linearly independent with the already chosen selected subset, then I keep it and I keep adding more elements. And at some point I will exhaust all the elements. Okay. However, this relies on something, this relies on we being able to list all the elements of real numbers. Well ordering theorem or equivalently axiom of choice. So there is yet one more way which looks more intuitive, but it is equally complicated and existential, that is using Zorn's lemma. And Zorn's lemma language uses partial orders. So that's why we studied partial orders. We'll see that tomorrow.